So today we are in chapter 4 and we are going to start talking about the slope of the tangent line. And so we have a little vocabulary that we need to start with here. Okay, so first of all, average rate of change is something we have already been doing. Okay, so this is the pre-calculus version of what we can do. And basically the average rate of change between 2 points is just the slope of the secant line connecting the 2 points. So this picture here, this is this is the average rate of change. So this is a picture of a secant line. So it's attached in 2 places here, okay? And the slope of that line is the average rate of change between when x is, I don't know, maybe a half here, and x is maybe a 4 here. And so if I wanted to find the average rate of change, I would just calculate the slope between those two x values. So I'd figure out what y was here and y is here, and I would take the y's on the top, right? M is y1 minus y2 over x1 minus x2. And that's all I'm doing. And so that's the average rate of change. And so that's what we have been doing already. And so now in calculus, we can now look at the instantaneous rate of change. Okay, so the difference between this is you can tell that the average rate of change here is different from the actual rate of change that's happening at, we'll say, at this point right here, right? The point at x equals a half. So it's different, right? It's not exactly the same right there. So it's an estimation of how much it's changing between those two x values. Where this is what we consider, right, the slope of the tangent line here. So a tangent line only touches my graph in the one place, just slides right up against it right there at that point. And that is what we consider to be the instantaneous rate of change. So it's not the average rate of change, it's exactly what we take to be the rate of change right there at that time. Because with curves, right, the rate of change is always changing. And so we need a way to figure out what the rate of change is right there at that time. Okay, and so this is the slope of the tangent line. And so we're going to talk about how we can find the tangent line. But before we do that, I want to give us a better picture here. Okay, so this is just a random curve. Okay, so this is just a downward parabola that I have here. And the red line right now is a secant line. Okay, and I have it attached here. The black point is at 0, 2. It's the y-intercept of my function. It doesn't matter what my function is. It just is a curve. And right now I have, so I want a way to estimate how fast my graph is changing right there at 2. So I need a way to estimate essentially the slope of the tangent line. So what we do is we pick a point that's near it. Okay, so now I'm using, basically I have my point 1 unit away from 0 here. So it's actually at x equals 1. And so the red line here, let me zoom in on it. The red line is the secant line, okay? And so we can use Desmos to estimate the slope of that secant line. So I've got it all set up here, okay? And so here I have f of 1 minus f of 0 all over 1 minus 0. And maybe you can see that, maybe you can't. It's 1.5 right here. So the slope, so the average rate of change between when x is 0 and x equals 1 is the slope, which I've just calculated, which is approximately, well, it's not approximately, the slope between those 2 points is 1.5. So that's not really that great of an estimate, right? I can see a gap here. So let's move our point, and we'll make it so that it's at a half. Do I have it at a half? All right, so now my point is only a half of a unit away. So let me zoom in a little bit again. Again, it's not perfect, right? Right around because I really want to estimate it right here at 2. It's not perfect, but it's a lot closer than the other one. And so let's find the slope between when x is 0 and x is a half. So I had that already set up. Oops, wrong button. And I have f is f of a half minus f of 0 all over 1/2 minus 0. And This time I come up with a slope of 1.75. And I'll show you the next slope as well. So when I move the point a little bit closer, right, I end up with, so if this is between the slope between the point 0, when x is 0, and when x is a fourth. So I just keep moving my point a little bit closer to where I want it to be. And this time my slope ends up being 1.875, okay? So what we're actually doing here, this sort of moving the point closer and closer, right? This is the idea of a limit. What we're doing is we're taking the limit of the slopes by moving it closer and closer and closer. So I want to show you the visual here. Oops, again, I did it the wrong place. I can actually make this, so I can make my h value change, and you can kind of see, so this is the slope of my secant line is changing. Now, right when h is 0, my graph is sitting exactly tangent. I'm going to stop it here and put it right at 0. So here, when h is 0, okay, so I don't know how I'm going to calculate my slope. I just kind of I'm going to have to figure that out in a minute here. But you can see that really when I zoom in here at 2, this isn't touching my graph any other place, right? Let me get it so that you can see it a little bit better. It's just touching the graph in that one spot. It's tangent to my curve at x equals 0. And when I zoom in really far, right, I really can't tell, right? The red curve is on top. That's the tangent line, and the black curve is the actual curve. And so when I zoom in really far, right at 2, my tangent line is essentially the same. It's lying right on top of it. And so that's why we can use the slope of the tangent line as our instantaneous rate of change. It's the change that's happening right there at x equals 0. Okay, so, well, that's wonderful, right? Now we know that the tangent line to a graph, we can estimate the instantaneous rate of change, okay? However, we still don't know how to find it. So let's talk about how we find it, okay? All right, so how do we find the slope of a tangent line with only one point, right? Because we've written equations of lines before, and they always require the slope and a point. Well, I only have one point, okay? So maybe this formula is going to look familiar here. So we're going to start with what we do know, okay? And so that is basically what we did before is, well, I can calculate the slope between the point and a little bit to the right or left. Now I'm going to just use to the right of it just because it's the easiest thing to draw, okay? And so what I'm going to do is I have these 2 points here. So let's say I want to find the slope of the tangent line to this specific point here, okay? And what I'm going to do is I'm going to just call this x, and the y coordinate that goes with it is just f of x, right? Because I just plug in x into f, assuming that I have f, and that's my x. So I'm going to put this other point, it's already here, and it's to the right of x, okay? So I'm going to draw this little triangle in here. All right, so this distance here, right, this is x right here. And this here, I want to call it with x, okay? So I want to say this is x plus a little bit more, right? It's to the right of x. And so I'm going to call this distance here h. So the h is just this difference between where this x coordinate is and where this x coordinate is. And so this x coordinate here is x plus h, okay? Now I want to calculate the slope between these 2 points, okay? So I'm going to call this point here x plus h, and then f of x plus h. I didn't do a very good job there. This parenthesis shouldn't be there. So this is the point x plus h, comma, f of x plus h. And this point down here is x, comma, f of x. And so we know how to calculate the slope, right? I can, if I imagine, right, that's my secant line through those 2 points. Maybe I should draw it a little darker. So let's write the equation of the slope of that. Okay? So my slope of this is, right, slope is y minus y over x minus x. So we're going to start with the bigger y. So I'm going to have f of x plus h, right? So I'm writing an equation between x f of x and x plus h f of x plus h, right? So that doesn't look like, I mean, I know they're kind of complicated looking points, but these are just my 2 points. So I'm going to call this x1, y1, this is x2, y2. And so this is y2 minus y1, so there's my y1, is f of x. And so I have this. Get a little focus better there. All over then x, so I started with y2, so I need to start with x2, so I have x plus h, then minus x1, which is x, right? This is just the slope. If you don't remember this formula, then you should go back and rewatch the equation on findings, or the lecture on finding slope. So this is how we write it. So my m is just f of x plus h minus f of x, and look what happens in the denominator. My x's, they cancel each other out and they leave me with h. So this is just the general equation for the slope anchored at x with another point just a little h distance away from x. So this is just the general slope. Now hopefully this looks kind of familiar, right? We called this before the difference quotient, and essentially it's just the generalized form of the slope between some point here x and then also some point here, and I've got it with h slightly to the right of x. Okay? Now what we were doing here is essentially the slope of the tangent line, we were sliding this point back along the curve and calculating slopes closer and closer and closer until we basically we're moving our point right on top of each other. And so hopefully that seems familiar when we're looking at how the graph is behaving right there. It's actually what we're doing is estimating the slope right there. And so we're actually taking the limit of the slopes. So what we want is essentially to eliminate this h altogether. So we're going to want, when we write our limit, we want h to approach 0 because we want this distance between these 2 points essentially to shrink into nothing. Okay, so I have the limit as h approaches 0 of f of x plus h minus f of x over h. And this is how we find the slope of the tangent line, is with this limit. Okay, so this is exciting stuff. This is the definition, essentially, this is what we call the derivative. Okay, so this is a new term made for some of you, I know. But the slope of the tangent line is really the same thing as the derivative at that point. Okay, and so let's just quickly run through a couple of some technical things. Okay, so this is what we call the derivative of a function. Okay, so, and the notation here is I have this little tick mark right here up above. That's not just a random mark. That's actually meant to be there. We say, the way that we say that is f prime of x. So f prime of x is the limit as h approaches 0 of f of x plus h minus f of x over h. Okay, so we say it f prime of x. So this is the derivative of a function provided the limit exists. Okay, and so some important things come out of this. And one of them is that f prime of a is the slope of the tangent line to a specific point, right? I just called it randomly a and the y-coordinate that goes with a. F prime of a is also said, it's the instantaneous rate of change at the point a, f of a. Okay, so we call it the slope of the tangent line, and we also call it the instantaneous rate of change. And then just a couple of other vocabulary words that go along with it is differentiation is just what we say, what we call the process of finding the derivative. And we say that a function is differentiable if the derivative exists at a point, or on the entire number line for the function as well. Okay, so if the equation is completely differentiable and the limit exists everywhere, then we say that it's everywhere differentiable. Okay, so some notations, common notations that we will use in this book is, I've already said, the f prime notation. So this one is f prime of x is how it's said. And this one here, this is Leibniz notation is what we call it. And this is said dy dx. It means the derivative of y, the function, with respect to the derivative, well, the variable x, okay? So the derivative of y with respect to the variable x is what this means. And then this is just another notation here where sometimes we say d dx because we can sometimes call y f of x, okay? And so this is just one last notation. So these are the ones that are most common to our book. Okay, so in the next lecture, I will do examples on how to use this.